Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hey everybody, I hope that you watched my video on what is mathematical induction, because we're going to need that here. I'm not going to really totally review it, although you do get somewhat of a review as we go through these proofs. So I've hand selected a few summation proofs here. So proving summation conjectures using mathematical induction is the idea. And somebody makes a claim. They say, hey, if you add up 1 and 3 and 5 all the way to the 2n minus first, where n is some number, a natural number, that should equal n squared. Now, before we go to prove this, I want to really tell you how important this claim is if it's true. It's telling me that if we add up, let's just take a look at for example, if n is equal to 10, this tells us if we add up the first 10 odd numbers, 7, 9, 11, 13, right? 15, 17. We'll end at 2 times 10 minus 1, which is 19. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 odd numbers there. That's the sum of the first 10 odd numbers. The claim is that's going to be 10 squared, or 100. Now that is pretty awesome. Just by itself, just that idea of adding up the first n odd numbers is going to be n squared. When somebody makes a claim like this, it's always fun to see, like, does it actually work? That is really cool if it does. And you're more than welcome to, try to sum that up and see that it actually is true. But we're going to prove it's true for any given natural number. So for all natural numbers really. Now, we don't want to go through and actually prove it for n equals 1, 2, 3, 4, 5, 6, 7, 8, all the way through the infinite amount of natural numbers, because, well, we don't have that amount of time. Ain't nobody got that time. So what we're going to do instead is mathematical induction. Let's go ahead and do the mathematical induction proof. And remember, it's a domino proof. So we're going to go ahead and start by saying, well, is the claim true for the first domino? Let's go ahead and prove that the claim they make there is true if n is equal to 1. So going back here, and I'm going to actually be as rigorous as possible about this. Now, personally, when I use a mathematical induction proof, I do not use propositional statements, but I know that most textbooks do. So I will do both here just to showcase. I'll start with how textbooks would do it. So they start with P of 1, the propositional statement, which is this claim right here. They're going to say, well, let's see if this is true for n equals 1. Well, let's see. We'll start at 1 plus. Now, if you let n equal 1 here, that means that summation would end at 2 times 1 minus 1, which is 1. So in other words, our summation's done. So the left-hand side is absolutely finished. The right-hand side is 1 squared, and the question is that true? And yes, absolutely. So if you let n equal 1 in this propositional statement, the left-hand side would be 1, the right-hand side would also be 1, and so this is a true statement. So we have proven that their statement, or their claim, their proposition, is true, at least for the first domino. Now, going back to the picture of our domino proof, which is proof by mathematical induction, we will then run down the line and assume that the proposition is true for some kth domino. So I'll just go down here and just say, assume the proposition is true for P of k. Now, I don't like to leave it there, because that can be very tough to work with if that's all you say. So write down what that means. What does it mean when you assume that this claim is true for n equals k? Well, it means that if you plug in k, it would be a true statement. So I like to actually write down what that means. I'm going to zoom in here. So our assumption just tells us that if we add up the first k odd natural numbers, it'll be k squared. That's what our assumption is. Now, what we want to do with that assumption is prove that once that kth domino, if we assume it's falling, we want to prove that the k plus first domino falls. So we need to prove that p of k plus 1 is true. It's really 3 steps to this. Step 1, prove that the first domino has to fall, or the statement is true for p equals 1. 2, which is the easiest one, assume that the statement is true for some kth domino down the line. So that is, your statement is true had you just plugged in k. And then 3, using that second statement, which is the induction hypothesis, prove that p of k plus 1 is true. So let's go ahead and do this. And by the way, in a proof, I would not number things. I like things kind of clean in a proof. And in fact, even in this is really not good enough, in my opinion, as a proof. Just the way it's written, it looks real clunky, but we'll clean that up a little bit later. So we're going to prove that the statement must be true for p of k plus 1. That is, we want to show, and this is what you're going to have to get used to in mathematics. You're going to have to get used to scratch work. So off to the side, I'm going to write WTS, which means want to show. I want to show that 1 plus 3 plus 5 plus all the way down the line, all the way to the k plus first, because we want to prove the statement is true for p of k plus 1. So we're going to add up the first k plus 1 odd numbers. So instead of n, we'll end at k plus 1. Now forgive me while I leave a little space there, and I'll say, okay, we want to end at k plus 1 rather than n. And we want that to be not n squared, but k plus 1 squared. We want to prove this statement is true had we replaced n with k plus 1. Notice that's what I just did. Now I left a little space there. Why? Well, what is the number right before k plus 1? It's k. So I want to write that in there because I've assumed something about that. So let me do that. I'm going to write in here 2 times k and then minus 1. This is basically this statement with a k in it. Okay. It's the statement, the odd number right before this odd number. And I want to include that because I made an assumption about that. I made an assumption about 1 plus 3 plus 5 all the way to 2k minus 1. So that will be very powerful for me. So let's go ahead, and it's important to say what you want to show just for yourself, not for your reader, but for yourself as you go to prove. You want to have that off to the side so you have a good, clear statement. Now back to the proof, I'm going to say 1 plus 3 plus 5 plus, I'm copying my blue handwriting over there, dot, 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 plus the quantity 2k minus 1 plus the quantity 2 times k plus 1 minus 1 is equal to. Well, again, this highlighted piece, we know from our assumption that highlighted piece is going to turn into k squared. And that's where the induction hypothesis gets used. You've made an assumption that that will turn into k squared. So I'm going to write that in here. This k squared. And then you still have off the back end this stuff right here. So I'm going to write that in. 2 times the quantity k plus 1 and then minus 1. All right, great. Now remember where you want to end up. You want to end up here. So let's see if we can manipulate this polynomial a little bit. This becomes k squared. Let's see, plus, I'm just distributing it out, 2k plus 2 minus 1, or in other words, plus 1. Now remember where we want to end up. I want to prove that left-hand side will turn into a quantity of k plus 1 squared. That's the whole point. I want this left-hand side to turn into a quantity of k plus 1 squared. Well, we know the highlighted piece turns into a k squared by our induction hypothesis. And then a little algebra gets us to this point. This leads to k squared plus 2k plus 1, and this factors to k plus 1 quantity squared, which is exactly, again, where we want to end up. This showcases that p of k plus 1 is true. So let's see, we've proven that the statement up here, the proposition, is true for the first domino, for n equals 1. We've assumed that it's true for some kth domino down the line, and then if it's true for that kth domino, it has to be, because we've just proven it, true for the next domino in line. Because k was arbitrary, it could have been 1, therefore the second domino has to fall. But because k was arbitrary, it could have been 2, therefore the third domino would fall. But since k was arbitrary, if the third domino is falling, then the fourth is falling, and so on and so forth. Thus, the claim is true for all natural numbers by mathematical induction. And that is the end of that proof. Now, to be honest with you, I personally don't like the structure of the way I've written this proof because it seems very algorithmic. And honestly, that's what proofs by mathematical induction are. You can't get away from that. But I do like a little more language in my proofs. So from this point forward, I'm going to actually structure my proof as follows. So again, we're just dealing with the same exact statement that the sum of the first n odd numbers is going to be n squared. So if I was doing a real proof, I would say it like this. 1 equals 1 squared is a true statement, therefore the claim is true for n equals 1. This is almost identical to what we said in the first statement up above. It's just a little more thorough with its and clean with its how it's claimed. And then I will say, suppose the claim is true for n equals k. Now, for the reader's benefit, and also for mine, I will tell them what that means. It means that 1 plus 3 plus 5 all the way to 2k minus 1 is going to turn into k squared. We're going to call that the induction hypothesis. Now I move on to proving that it must work for n equals k plus 1 by saying, well, if we consider the next domino in line, n equals k plus 1, we have the following: 1 plus 3 plus 5 all the way down, and I'm going to go ahead and include that 2k minus 1, the kth domino, but also the k plus first domino, because, well, that's what we're assuming. We're not assuming, but that's what we're working for. We're considering the k plus first domino. And that is equal to k squared plus 2 times the quantity k plus 1 minus 1, and I will go ahead and put a comma by the induction hypothesis, and I think it's actually pretty safe here to say by I.H, induction hypothesis. And this is equal to k squared plus 2k plus 1, which is equal to the quantity k plus 1 and quantity squared. And that shows us that if we add up the first k plus 1 dominoes, yep, that'll be k plus 1 squared. I just make that little extra statement. The claim is therefore true for the k plus first domino, and that tells me the claim is going to always be true. Whenever one domino falls, we've proven the next one has to. And I just polish up the end and make sure that everybody knows that I'm stating the actual claim that they made is actually true. Hence, the claim is true for all n in the natural numbers. That's what that upside down capital A is, this guy right here. It means for all. Let me go ahead and point at it and just say for all. You'll see that in symbolic logic, so you might as well just start using it now. So that's how I'm going to write my proofs. They just are a little beefier, a little better, I think. They're mathematically more elegant. Well, I don't know if that's true, actually. I would say that they do look better in my eyes. So that's how I'm going to do my proofs. Let's go ahead and try another one. Prove that the formula is true for all n in natural numbers. This is a very famous formula, by the way. This is a formula attributed to Gauss way back when, and I'm sure this is sort of an embellishment on how he proved this is true, but the story goes that he was given busy work when he was a young child by a school teacher The school teacher actually gave all the students busy work. And if you look at this claim, it's telling us if you add up, let k equal 1, and then 2, and then 3, and so on and so forth. If you add up all these numbers, all the way up to n. I'm going to stop at 100, though, because that's, I think, what the busy work that was given to Gauss. Anyway, you add those up, it's going to be 100 times 101 divided by 2. So it's the sum of the first n natural numbers is going to be n times n plus 1 over 2. How Gauss, again, this is how the story goes. Stories are different than reality, so I'm not 100% sure this is actually true, but if it is, it's pretty awesome. How Gauss supposedly did it is he had all the numbers listed out. He just wrote 1, 2, and he got kind of bored, got to here, let's just say, and he decided to go backwards. 100, 99, 98, I'm bored there. Maybe I should go to the middle. And then he went to, let's do 49, 50, 51, and 52. There we go. And he folded his paper in half. And then he noticed, again, this is as the story goes, when you add those two numbers, they're 101. And when you add these two numbers, they're 101. Huh, that's interesting. Next two numbers add to 101. These two numbers add to 101. These two numbers add to 101. And the final two numbers add to 101. Interesting. And how many groups of those are there? 50 of them. 50 times 101 is 5,050. So that's how he presented this. He just said, 5,050 or whatever. And again, as the story goes, his teacher was shocked, thought he did something weird or whatever, and couldn't figure it out. Later on, he proved this statement was true, as we shall right now. So let's go ahead and go to make this statement as true as possible in our eyes as we can. So the proof goes like this. Proof. Now I'm going to go ahead and say, it might help you out, by the way, to write out the summation a little bit. So it's 1 plus 2 plus 3 plus ... all the way to n. And we're claiming that's going to be n times n plus 1 over 2. It's just, I think, a lot cleaner for students to do that. So write it out as an actual expanded sum. For n equals 1, you see that 1 is equal to 1 times 2 over 2. That is true. It's, well, even, let me copy the formula. It's exactly. So if you let n equal 1, the left-hand side, you'd only sum up the first element. The right-hand side would be 1 times 1 plus 1 over 2. And that is a true statement. This is 2 over 2, which is equal to 1. Thus, the claim is true for n equals 1. We've proven that. And so now we're going to go ahead and, now that we've knocked over the first domino, we'll go ahead and say, well, suppose that the kth domino is falling. And this is another reason why I decided to expand the summation out, because if I kept with that summation, you can see there are k's in that summation, and that gets annoying for my eyeballs. I don't want two different variables in my statement. So instead, I just write it like this, and I can ignore the k in their summation index. All right. So let's assume the claim is true for n equals k. Now you are reading this. You should be led a little bit. Somebody, specifically me, who's writing this, and you, when you're writing it for your professor for homework, you should actually explain to the reader what this means. So I would say that is, and then I would write down the summation all the way up to k. 1 plus 2 plus 3 all the way up to k should turn into k times k plus 1 over 2. And we're going to call that the induction hypothesis. Now we want to show, using that argument, using that assumption, I should say, we want to show the claim is true for the k plus first domino. That is, so this is not what you're going to show a reader. This is what you're going to do for yourself. You want to show that 1 plus 2 plus 3 plus ... all the way down the line to k plus 1. Notice how I left a space there. The reason why I left a space there is because what number comes before k plus 1? K. So I added up 1 through k and added on one more. And that is we want that to turn into this statement with k plus 1s instead of n's. So k plus 1 times k plus 1 plus 1, or k plus 2, all over 2. We want to show that. I keep that off to the side so that nobody sees that. And I hop back over here and I just say, okay, well, let's see. We've proven it's true for 1. Therefore, the claim is true for 1. We're going to assume the claim is true for the kth domino. That is, we have some kth domino that's falling over so that the claim they're making is true all the way up to k, or for the kth domino, I should say. And now we're going to consider n equals k plus 1, the next domino in line. Well, if that's the case, we're looking at 1 plus 2 plus 3 all the way down the line to, remember, I'm going to steal my handwriting from over there in the blue area, adding all that stuff up. However, I'm free to say this bit right here and this bit right here are the same. We've assumed 1 plus 2 plus 3 all the way up to k is going to turn into k times k plus 1 over 2. So I'm going to go ahead and say this is equal to k times k plus 1 over 2 plus that additional little k plus 1 that's still hanging out there waiting for me to do something. And I'll just put a comma by induction hypothesis. And now that I'm down to something really easy to work with, I'll look at what I want to end with. Notice in blue over there what I want to show. I want to show that that will turn into k plus 1 times k plus 2 over 2. Notice both of these terms have a k plus 1 in common. So I'm going to factor that out of both those terms, factor it into the front there, and I'm left with a k over 2 plus 1. Well, common denominator is 2, so that's going to be a k plus 1 times a k plus 2 over 2. And I can factor, or I can rewrite that, I suppose, as a k plus 1 times k plus 2 all over 2, which is exactly what we wanted to show. We wanted that 1 plus 2 plus 3 all the way to k plus 1 to become k plus 1 times k plus 2 over 2, which we have done. Thus, the claim is true for n equals k plus 1. Let me zoom in and say that. There we go. Thus, the claim is true for n equals k plus 1. And so, the claim must be true for all natural numbers by mathematical induction. Again, we've just shown that if we assume that the kth domino is falling, the k plus first must be falling as well. The claim works for k plus 1, assuming the claim works for k. And we've proven it works for 1, so k could be 1, that means it has to work for 2. Now that it works for 2, it has to work for 3. Now that it works for 3, it has to work for 4, and so on and so forth. QED. So that is the end of that proof. So you can see they're all kind of this way. By the way, this specific summation comes up in calculus quite a bit, and pre-calculus, I should say. So you're going to be dealing with that summation quite a bit from this point forward in mathematics. Not all the things we prove in this video and in mathematical induction get used over and over again, but that one specifically does. And so does this one. All right, so this one tells me that if you add up all the squares, 1 squared plus 2 squared plus 3 squared, and in fact, that's how I'm going to write this, 1 squared plus 2 squared plus 3 squared, and so on and so forth down the line until you get to n squared. The claim is that should be n times n plus 1 times 2n plus 1 all over 6. That's the claim. We want to prove that. Okay, let's go ahead and do it. Proof by mathematical induction. Proof. Well, if you let n equal 1, the left-hand side just stops at 1 squared. And that is equal to 1. We definitely know that. And that's going to be, let's see if that's the same thing as the right-hand side. Is that 1 times 1 plus 1 times 2 times 1 plus 1 all over 6? Well, I don't know. That's going to be 2 times 3 over 6. Yep, that's definitely 1. Thus, the claim must be true for n equals 1. Now we're going to go ahead and assume that this claim works for n equals k. And when we make that assumption, it's really good for us to state for the reader what that truly means. It means the sum of the first k squares, 1 squared plus 2 squared plus 3 squared all the way to k squared, is going to be k times k plus 1 over 2k plus 1, all divided by 6. All right, great. Now we're going to go ahead and go to that next domino. If we assume that the claim works for n equals k, I'd love to prove, therefore, that it works for n equals k plus 1. Now, when I do this, I immediately think, oof, I have to write down where I want to go. Because if I don't do that, I might kind of go off the rails here. So let me go ahead over to the right-hand side and then just tell myself where I want to go. What do I want to show? I want to show that 1 squared plus 2 squared all the way up to, I'll leave a little space here, all the way up to k plus 1 quantity squared. I want to show that that is equal to, and I didn't give myself enough room, so I'm going to go ahead and grab this and move this over a little bit. I want to showcase that that is equal to k plus 1. Oh, let me go over here. I'm going to substitute in to this, and for the ends, I'm going to substitute in k plus 1. So it'll be k plus 1 times k plus 2 times 2 times the quantity of k plus 1 all over 6. So let me write that down. It's k plus 1 times k plus 2 times 2 times the quantity of k plus 1 all over 6. That was just me substituting in k plus 1 in for those ends right here. That's where we want to end up. Now, I left a little space in that blue ink because really right before k plus 1 is the kth term. And this piece right here is our induction hypothesis. We know, we've assumed that that turns into something. So that's going to help us quite a bit. All right, so going back to the proof. Consider n equals k plus 1. Well, great. Somebody's reading this. They say, okay, they're going to add up the first k plus 1 squares. So 1 squared plus 2 squared plus 3 squared. And they're reading your proof and they see that you go to k squared for some reason and then the k plus first term. They're like, why do they do that? And then you highlight and say, well, this stuff right here is this stuff right here. And we've assumed that that turns into this stuff right here. So you're going to say this is equal to k times k plus 1 times 2k plus 1 all over 6. And then don't forget, you still have this k plus 1 to the second power term right here that's waiting to be written. And I'll just tell the reader that was by the induction hypothesis so that they know where I got that from. Now, remember where we want to arrive. We want to arrive at this statement right here. And this statement, by the way, if you clean it up a little bit, it's k plus 1 times k plus 2 times 2k, was it plus 3? All right. All over 6. So I know where I want to end up. K plus 1 times k plus 2 times 2k plus 3 all over 6. Notice both of these terms have a k plus 1. I'll at least start there. I'll factor out a k plus 1. When I do that, I'm left with a k times a 2k plus 1 all over 6 plus a k plus 1. Remember where we want to end up. We want to end up with a denominator of 6 for everything. So let me go ahead and just force a denominator of 6 inside here. This is k times 2k plus 1 plus 6 times the quantity k plus 1 all over 6 now. Okay, we're getting close, but no cigar. We're going to have to go ahead and multiply out that stuff in the numerator. It looks like it's a little bit of a mess, but not terrible. The numerator will become a 2k squared. let's see, plus k plus another 6, so plus 7k. And then let's see, plus 6. It's all over 6 now. And this will factor k plus 1 to k plus 2 times 3k plus, nope, that will not factor that. It'll be k plus 2 times 2k. I was like, what's going on there? 2k plus 3. Let's double check that. That's 4k. That's 7k, definitely. And 6 and 2k squared. So that works. All over 6. And you could zoom out and you could, I suppose, even though we've done this off to the side, you might want to convince your reader that this is actually a k plus first term. Or this is what you would want had you plugged in k plus 1. Some people do this, some people don't. I'll go ahead and do it. I'll say, but that is equal to k plus 1 instead of a k times k plus 1 instead of a k plus 1. And this is 2 times k plus 1 plus 1. The reason why I'm doing that, let me just highlight so that you can see. I'll highlight all the k plus 1s. Everything that I've highlighted is what n would have been up here. n plus 1, 2n plus 1. Instead of n's, we have k plus 1s. k plus 1, k plus 1 plus 1, and 2k plus 1 plus 1. It's hard to say. But anyway, those are playing the role of n. That is, we have proven it works for k plus 1. When you add up the first k plus 1 squares, it turns into that. Thus, the claim is true for n equals k plus 1, and so the claim is always true for all natural numbers n by mathematical induction, QED. That is a good mathematical induction proof. Notice my structure, how I always start, if somebody hands me summation notation like this, I rewrite it as an actual sum just because it's a little bit easier for me to work with. First step is always proving that it works for 1. Second step is always to assume that it works for k. And third step is to use that assumption to prove it works for k plus 1. So here's our last one. And this one I actually, there was a little typo. I started doing this and then I realized, wait, there's something weird with this. There's a typo in my notes. So this one I have never proven before. Every other problem that we've done in this video, I have actually proved in semesters past. I've been teaching forever, so this stuff I just know. However, this is one I've never really proved, and I thought it'd be kind of nice for you to see how my mind works or how you should be working when you're working through something the very first time. So you'll see there's very little difference between all the previous examples in this of how I operate. So to prove this is true, luckily this is not a summation. I mean, it is a summation, but they didn't use a sigma notation, so it's already expanded for me. I'm going to go ahead and start with n equals 1. Now, if n is equal to 1, you would get 1 times 2 in the denominator, which is actually just this first term. So I just double check that first. I say, okay. Note that 1 over 1 times 2 is 1/2. Great. And that is the same as 1 over 1 plus 1. I'm substituting in ones for these n's right here. So when I get that, that's definitely 1/2. Absolutely. Check. That is true. Thus, the claim must be true for n equals 1. And now, just like all the previous examples, I'm just going to suppose that it works for n equals k. That is 1 over 1 times 2 plus 1 over 2 times 3, all the way down the line, all the way to 1 over k times k plus 1. That's going to equal k over k plus 1. Notice that my language, I don't always say the same thing, right? I think in the previous examples I said, assume the claim is true for n equals k. And another one I said, suppose the claim is true for n equals k. And now I'm saying, suppose the claim holds for n equals k. You could be as artistic as you want with the language because you don't want to be formulaic all the time. That's not very fun. So now we're going to go ahead and see what happens with n equals k plus 1. And notice I'm using, again, different language. In the case that n equals k plus 1, we get the following, right? By the way, I should note this is my induction hypothesis, just for the reader. I'm going to be using that in a moment. So let's see. Off to the side, like any good mathematician will do, we just write down where we want to go, what we want to show. Well, we want to show that if we substitute in k plus 1, this will work. That's what we want to show. So we want to show that 1 over 1 times 2 plus 1 over 2 times 3 all the way down the line until we get to, I'll leave a little space there, 1 over, instead of n, we'll put in k plus 1s. So k plus 1 times k plus 2, right? That's, had you substituted in k plus 1, that's what you would get. K plus 1 times k plus 1 plus 1, or k plus 1 over k plus 1 times k plus 2. And we want to show that that is equal to k plus 1 over k plus 2. And the missing element I didn't write in is the term right before the k plus first term, which is the kth term. And the reason why I include that is because that is our induction hypothesis. So I know kind of what I'm going to do. I'm going to replace that highlighted stuff in a moment with a k over k plus 1. So in the case that n is equal to k plus 1, we have the following: 1 over 1 times 2 plus 1 over 2 times 3 plus all the way down the line until you get to the kth term, 1 over k times k plus 1, and then the k plus first term, 1 over k plus 1 times k plus 2. And we know that this picture right here, by the induction hypothesis, will turn into k plus 1. K over k plus 1, I apologize. So this is k over k plus 1. And then we still have that plus 1 over the quantity k plus 1 times the quantity k plus 2. But this is true by the induction hypothesis. Now we can actually combine those two fractions, and noting where we want to end up. We want to end up at k plus 1 over k plus 2. So I'm going to go ahead and combine these two fractions by using a common denominator. That's k times k plus 2 plus 1 over k plus 1 times k plus 2. If it doesn't look like it's going to get where we want to go, you just have to cross your fingers and hope. Honestly, that's k squared plus 2k plus 1 all over k plus 1. If the claim is true, it will work out. You just have to hope. You have to hold on to that hope. It's k plus 1 squared in the numerator. Downstairs you have a k plus 1 times a k plus 2. And note the k plus 1s will cancel and you'll be left with a k plus 1 over k plus 2. And just in case, notice that's where we want to arrive at. We want to arrive at k plus 1 over k plus 2. Just in case our reader needs it, they shouldn't, but just in case they do, I'll note that where we need to lead our reader to is us saying it's k plus 1 over k plus 1 plus 1, just so that our reader knows that we have just proven something cool. So I'm going to do that. This is equal to k plus 1 over the quantity k plus 1 plus 1. And thus, the claim is true for n equals k plus 1. That is, if once we added up the first k plus first terms or k plus 1 terms, it ended up being that the claim was true. It turned into k plus 1 over k plus 1 plus 1. And so I will make that clear. The claim works for n equals k plus 1, and so it is true for all n in the natural numbers by mathematical induction. QED, end of proof. And again, that's the first time I've proven that. So even though I've never proven that specific one before, they all kind of run the same way. Just prove it works for n equals 1, assume it works for n equals k, and use that assumption to show that it works for n equals k plus 1. Pitfalls that I'll commonly see students making mistakes on is that when they write what they want to show here, they feel like, I've seen students that do this, they feel like that just proves something. That proves nothing. You want to get there. But a lot of students, when they write out this step, oh, in the case that n equals k plus 1, we get this summation right here. Then they just say, oh, and that equals, because they're copying their work over there. And they'll say that equals k plus 1 over k plus 2. That's not true. You have to show that it equals k plus 1 over k plus 2 by using logical deductive argument and mathematics. So if you have a very short mathematical induction proof, you've probably done something wrong. That's pretty much how it goes. All right, I'm done with this video. So in the next video, we'll do mathematical induction proofs that don't involve summations.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't